Let us look at another example to draw the Nyquist plot to investigate the stability of the system. The problem statement goes like this. Draw the Nyquist plot for the system whose open loop transfer function is given by GH of S is equal to 1 plus 0.5s divided by S square into 1 plus 0.1s into 1 plus 0.02s, and find the closed loop system stability. So in this case, k is not given, therefore we need not find the range of k. So whatever the k that is available, in this case it is 1 for example. So what will be the system stability, whether stable or unstable or marginally stable? Let us investigate using the Nyquist plot. Now if you look at the open loop transfer function, it is a type 2 system, and of course we have 0 in this particular case. It's a type 2 system. When you have type 1 or type 2 system, then what will be the Nyquist path? The Nyquist path will contain 4 paths. That means we need to take the path 4 also, so because there are poles at origin. Now what is the path 1? The path 1 is when omega is varying from 0 plus 2 plus infinity. Then what is path 2? The path 2 is the radius r tends to infinity and it is from plus 90 to minus 90. And similarly, what is the path 3? Path 3 is a minus infinity omega varying from 2 0 minus. Then what is the path 4? Again here the radius is going to be r tends to 0, a very small semicircle. The angle is from minus 90 to plus 90. So this is a complete Nyquist path which is available in the S-plane. Now Nyquist plot is the mapping of these 4 paths into GH plane. So first one is path 1. The path 1 the results in polar plot when you map into GH of S plane. Then how to draw the polar plot for this particular open loop transfer function? Take the transfer function GH of S, which is already available to me, 1 plus 0.5s divided by S square into 1 plus 0.1s into 1 plus 0.02s. Substitute S is equal j omega, get the sinusoidal transfer function. So that is, you can say 1 plus j 0.5 omega divided by, we have j omega square, again 1 plus 0.1 j omega into 1 plus 0.02 omega. Magnitude and phase angle we need to write. The magnitude is going to be numerator, it is under root 1 plus 0.5 omega whole square, and divided by, here I have omega square in the denominator, and 1 plus 0.1 omega whole square, and under root again 1 plus 0.02 omega whole square. What will be the phase angle? The phase angle is numerator I have tan inverse 0.5 omega, and when it comes to denominator S square term we have, for j omega square it is minus 180, and the next term is minus tan inverse 0.1 omega minus tan inverse 0.02 omega. So this is what the phase angle expression. Once you have the magnitude and phase angle expression, then we can draw a table where we can have the 4 entries in this, which is enough to draw the polar plot. Now omega is 0 I am taking. What will be the magnitude? The magnitude is infinity because it is a type 2 system. Again, what will be the magnitude when omega is infinity? It is 0. Then what are the phase angles which are important to draw the polar plot? So the first phase angle is, when omega is 0 it is going to be minus 180 degrees. But when omega is infinity, the angle is minus 270 degrees. So minus 180 to minus 270 we need to have the polar plot. But in between I am going to take 2 more values. When omega is very less value, that is 0.01 for example, then what will be the angle? When you look at the angle, it is minus 180.1. So when you look at this very small value, so the small value is going to be 179.9. When you take the large value, it is going to be minus 269.9. So in between, when you look at the values from 182, it is going to minus 179 and so on. Then after that it is entering to the second coordinate and it reaching to minus 270 degrees. So when you plot into the polar plot, let us look at the polar plot here. So 180 is the starting point, this is 180 degrees line. But thing is whether we need to take above the line or below the line, the starting point. So in this case we should take the below the line because 0.01 it is minus 179. So this is the starting point. The ending point is at origin, but when it is approaching to origin, it has to cross minus 270 degrees line. So this is the starting and this is ending. So when you sketch it, then it will be like this. So this is okay. Then it is crossing minus 180 degrees line once here. So if at all, if this at 0.01, then angle is above minus 180 degree, let us say minus 181, minus 182, then in that case, so this polar plot, it never crossed this minus 180 degrees line. But in this case, since it is minus 79 point something, which means there are values which are in the third coordinate. So this is very important because this will decide the stability of the system. So I have like this now. Fine. So what is this? How many times it is crossing minus 180 degrees line? Once. If at all, if you solve for omega PC, if there are more number of omega PCs, that means let us say there are 3 omega PCs. So this particular polar plot will intersect the minus 180 degrees line multiple times. The number of times which is equal to the number of omega PC values when you solve for this transfer function. So we will see that how to solve omega PC, but the results only one omega PC. Therefore, I am going to plot like this for polar plot. This is a path 1. When it comes to path 2, we know it is one or more semicircles around the origin with r tends to 0, which can be ignored very easily. Then path 3 is the inverse polar plot. We already have the polar plot. The inverse polar plot will be like this, but direction should be continuous. So here direction towards the 0 origin, now the direction away from the origin. This is path 3. Then what is the path 4? Since I have 2 poles at origin, there exists path 4. Path 4, the first thing is how many poles that are there at origin. There are 2 poles. Means you need to have 2 semicircles. 2 semicircles form a circle, in fact. So 2 semicircles. Now what is the starting point of the path 4? The starting point of path 4 is the ending point of the inverse polar plot. We know the ending point of the inverse polar plot is above the 180 degrees line. This is the ending point. Then the ending point of path 4 will be the starting point of the polar plot. Starting point of the polar plot is here below the 180 degrees line. Starting point of the path 4 is here, ending point of path 4 here, and there are 2 semicircles we need to draw, and the direction is always a clockwise direction. And what will be the radius of it? The radius of it is r tends to infinity. So I will start here, then I take a circle like this and I'll come back to this point. So already we have polar, inverse polar, and along with that I have the path 4, which gives the complete Nyquist plot. So now once the Nyquist plot is available, then how to find the stability of the system? To know the stability of the system, we have to use the formula, that is Z is equal to P minus N. So when you look at P in this particular system, there are no poles of open loop transfer function lying in right above this plane. P is 0. Then find out N. So polar Nyquist plot is available. From that we will try to find how many number of encirclements around the origin in anti-clockwise direction. For that we must know the intersecting point. So how to get this intersecting point? It's very simple. Take the phase angle expression, equate it to minus 180 degrees. So when I equate it to minus 180 degrees, then we have already tan inverse 0.5 omega minus 180 minus tan inverse 0.1 omega minus tan inverse 0.02 omega is minus 180. So when you solve it, you will be getting the omega value as 0.11. So 0.11 is the omega value. Then corresponding when you substitute in omega magnitude, the magnitude is also I am getting 0.11. So the magnitude is 0.11, which means the point where it is intersecting is the 0.11. This is a magnitude from 0 to this point is 0.1. What will be the point? It is a minus 0.11 plus J0. This intersecting point is minus 0.11 plus J0, and the corresponding omega PC is, we already seen it is 19.5 radian per second. At 19.5 radian second, I have the magnitude like this. Now, so where will be the critical point? The critical point is away from it, not inside the circle, away from it. Here I have the critical point. Draw one line. When you draw one line towards the left direction, then how many intersections have? Two intersections, out of which the first one is anti-clockwise and the second one is clockwise. So anti-clockwise and clockwise, the number of encirclements is going to be 0. If number of encirclements 0 and P is also 0, then Z is equal to also 0. So Z0 indicates the closed loop system is stable. Hence we can say that using Nyquist plot, the closed loop system of given open loop transfer function will be a stable condition.